She's spinning too fast. What's it going to do? Oh, we'll just let it go. We'll let it run.
They might pull each other.
There we go. Woo. Okay, so here's the problem, right? Here's the problem, right? As far as I could tell, almost any nebula has some amount of, just by its happenstance, has some amount of net angular momentum, just because of the random motion of it. And if you collapse any cloud down there, basically it's going to add up. Okay, it's going to add up to one axis of rotation and one amount of angular momentum. So all the random motion will just get added up, and you'll get the net vector sum of all the rotation in the cloud. And almost any cloud has too much rotation to ever give birth to a star. Yet, stars are being born. We can see them being born. So what is the mechanism by which these things are able to slow down? There's no friction. There's no, right? There's nothing. It's in space. It's floating in space. It is perfectly frictionless. It should spin forever and never give birth to a star. And so what they actually started noticing was that these really rapidly spinning stars, or about to be born stars, started shooting off these little jets. They generate powerful magnetic fields. That we think those magnetic fields pump energy into these jets, and that these jets spin dramatically. So here's a picture of this is the Trifid Nebula, right? And if you look at this, see that little jet there? Yeah. Kilometers per second, tens of kilometers per second. This material is, we've run into an internal limit in interactive physics, right? Okay. But that little thing right there, okay, is a jet, and it's shooting out, and there's places where we can see them shooting in both directions. They're bipolar jets, right? Okay. And it's shooting material there, and we think the mechanism is that it's actually the magnetic field spins the material in those jets faster than the protostar is spinning. So therefore it's jettisoning, not only is it jettisoning material, but it's also jettisoning angular momentum. It's slowing itself down. That's a method for slowing yourself down, is that you spin something else up in the direction you're going and throw it off, right? So if you're on one of those gates at IBII Park and you want to slow down, you're like, help, please slow down. You could, if you had like a little drill, spin something the direction you're going, throw it off. Every time you spin it up in the direction you're going, you slow down because angular momentum is conserved. Yeah? Right? So if you speed it up, it slows you down. Right? I know. It's like, there, I'm slowing down. You're like throwing these spinning discs off of it. Right? Okay. And then we've got to see what interactive physics is doing. Oh, come on, just keep going. Just continue, baby. Oh, it's gone. It's off the screen. Stop, reset.
Yeah, look.
Pass your partner on the left.
Hey, look, there's 4 stars. Hey, it's running a lot faster this time.
Well, it's because it's just playing the movie. I love that one. Pew! That's all it does. So it's spinning so fast that it just does a little do-si-do and flies off. Right? And this is because of the remarkable symmetry. This isn't any real sort of thing.
Like that maybe? He's got a moon launch it, though.
Yeah, there he goes. Yeah. Yeah, it could, right? This is not realistic. This is like perfect symmetry. That's why I made 4 different things, right? But it's on there. It's in the lecture folder, and if you have interactive physics, if you want to mess with it sometime, you could.
Can you change the spin so it's not even on all 4 sides?
Yeah, you could do that. Do it. We're going to do this, right? Okay. Then the thing to notice here, just for fun, okay, also notice this nebula. See that little pillar right there? You see this guy? You see that? That little guy is not a jet. That guy's actually what's called a pillar. Pillars are where there's a supergiant star that's shooting photons and electrons and charged particles, just something called a solar wind, and it's blowing this nebula away, right? Doesn't it look like this nebula is all going this way? Yeah, it's because the radiation pressure of that star is pushing all of this stuff down. This is a little knot of material, okay? And that knot of material is protecting the stuff below it. Just sort of like after a rainstorm, you find like a bark chip on a little pillar of dirt, right? It protected the dirt below it from the rain, right? It's the same thing. Here's another little pillar over here. These might become little solar systems, right? So it eventually slows. We get fusion. Oftentimes, the first star born blows the nebula away, right? It's like the first chick to hatch kills all the other chicks. Isn't it? What bird does that? It's like the mockingbird. What's the one that lays its eggs in? The cuckoo does this, right? This is like the most violent type of thing, right? You lay your egg in some other bird's nest. When your chicks hatch, they hatch first, and they kill all the other right? In their, you know, before they can get born, and then they're like, hey, feed me, right? This giant bird, right? You know. And then what's left over, what doesn't become the star, circles the planet like an accretion disk. This is like the rings of Saturn, right? An accretion disk, think rings of Saturn. And there's lots of rings like this. And disks basically form because if anything's not in the plane of that disk, it's going to strike the disk, isn't it? Yeah? Think of something that's orbiting. Everything is orbiting this way. If you're trying to orbit this way, it's kind of hard to, isn't it? You're going to run into that disk and eventually join the debris that's in that disk and maybe change the angle of the disk a little bit. So that's why disks form, and you'll see them. Black holes have disks around them, planets have disks, and new stars have something called an accretion disk. Accretion just means to add on to, and disk means disk, right? Here is, this is 500 astronomical units, so that's like a solar system size. Here is a new protostar where part of the light from it is blocked by some band of dark material. Probably we're seeing an accretion disk edge on, right? So these are newly forming stars, and that's the best one for the purposes, right? But there we go, young stellar disks, infrared. And we're looking at this in infrared light because infrared light can travel through clouds of dust unimpeded. Right? It's got a big enough wavelength that it's not reflected by tiny particles of dust, whereas visible light is easily reflected. Right? So this is your brain on physics. Right? No, just kidding. Here's the accretion disk. This is supposed to be the yolk of, no, that's the sun. Right? There's the new star. There's the rocky stuff. And here's the icy and gassy stuff, right? In an accretion disk, we expect the stuff close to the star to not have a lot of ice because it's hot close to the star, yes? Farther away from the accretion disk, you might find ice and gas because that's where it would tend to settle and condense. Yeah? Yeah, I guess. Like Jupiter. Think Jupiter, right? Okay. So if we look at our own solar system, the inner planets are rocky. They are terrestrial, yes. Okay, and then the outer planets are gassy, right? Right. Here are the outer planets, right? These are all very far from the Earth, and the farther they get, the more icy they get. The closer they are, the more gassy they are. Oh, sorry. Okay. Here are gaseous pillars again. These are pillars, and then the pillars have pillars. Right? So there's a giant star up above there that's blasting all this stuff down this way, right? And these little pillars are the places where the stuff is locally accreting and becoming protostars. There. You see all those little things? And then this itself is a pillar. Here's another pillar. These are places where solar systems, so this is like the size of a solar system in there. This is quite large, right? Isn't that beautiful? I think that's cool. Right? Here are a couple galaxies colliding, and these are supergiant stars that have just got born. We know they just got born because they don't last long. They last like a tenth of a billion years, right? And our star is going to last 15 billion years, so you know, there we have it, right? So these things, these two galaxies, if you could see this in like God time or something like that, right? Okay, these things would come together, they come flying together, they do this crazy little pirouette, right? And and they, yeah, I know, it's like play it fast, right? These things would be like little firecrackers just going bam, 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 right? And then some stars that last a long time are born as well, but supergiant stars are born, and that's because large clouds of gas and dust are collapsed because of this violent impact of the galaxies. They were, a lot of clouds can just sit there and spin around each other and not collapse, right? But the impact of these two galaxies caused a lot of these star births. And then this is, you know, basically spiral galaxies are just like washing machines, right? Any kind of spiral is like a washing machine. It's an agitator. It sits there and grinds away at the stuff that's in it, and 100 stars are born every second or something in one of these galaxies, right? You know, so these things have a constant rate of star birth, whereas elliptical galaxies not so much, right? So here's the center of our galaxy. And this is, I believe, our infrared, I think, camera, right? And so near the center of our galaxy, there are stars being born, and indeed near the centers of any galaxy, right? So here's another star birth region. And you can see there's clouds of stuff hydrogen and other molecules, right, that are left over from stars that are going to eventually accrete. And